In computability theory, the halting problem is the problem of determining, from a description of an arbitrary computer program in an input, whether the program will finish running or continue to run forever. Alan Turing proved in 1936 that a general algorithm to solve the halting problem for all possible program input pairs cannot exist. A key part of the proof was a mathematical definition of a computer and program, which became known as a Turing machine. The halting problem is undecidable over Turing machines. It is one of the first examples of a decision problem. Jack Copeland attributes the term halting problem to Martin Davis. Background: the halting problem is a decision problem about properties of computer programs on a fixed Turing-complete model of computation, i.e., all programs that can be written in some given programming language that is general enough to be equivalent to a Turing machine. The problem is to determine, given a program and an input to the program, whether the program will eventually halt when run with that input. In this abstract framework, there are no resource limitations on the amount of memory or time required for the program's execution. It can take arbitrarily long, and use arbitrarily as much storage space, before halting. The question is simply whether the given program will ever halt on a particular input. For example, in pseudocode, the program while continue does not halt, rather, it goes on forever in an infinite loop. On the other hand, the program print, "Hello, world" does halt. While deciding whether these programs halt is simple, more complex programs prove problematic. One approach to the problem might be to run the program for some number of steps and check if it halts. But if the program does not halt, it is unknown whether the program will eventually halt or run forever. Turing proved no algorithm can exist that always correctly decides whether, for a given arbitrary program and its input, the program halts when run with that input. The essence of Turing's proof is that any such algorithm can be made to contradict itself, and therefore cannot be correct. Importance and consequences. The halting problem is historically important because it was one of the first problems to be proved undecidable. Subsequently, many other undecidable problems have been described. The typical method of proving a problem to be undecidable is with the technique of reduction. To do this, it is sufficient to show that if a solution to the new problem were found, it could be used to decide an undecidable problem by transforming instances of the undecidable problem into instances of the new problem. Since we already know that no method can decide the old problem, no method can decide the new problem either. Often the new problem is reduced to solving the halting problem. For example, one such consequence of the halting problem's undecidability is that there cannot be a general algorithm that decides whether a given statement about natural numbers is true or not. The reason for this is that the proposition stating that a certain program will halt given a certain input can be converted into an equivalent statement about natural numbers. If we had an algorithm that could find the truth value of every statement about natural numbers, it could certainly find the truth value of this one, but that would determine whether the original program halts, which is impossible, since the halting problem is undecidable. Rice's theorem generalizes the theorem that the halting problem is unsolvable. It states that for any non-trivial property, there is no general decision procedure that, for all programs, decides whether the partial function implemented by the input program has that property. For example, the property halt for the input 0 is undecidable. Here, non-trivial means that the set of partial functions that satisfy the property is neither the empty set nor the set of all partial functions. For example, halts or fails to halt on input 0 is clearly true of all partial functions, so it is a trivial property, and can be decided by an algorithm that simply reports true. Also, Note that this theorem holds only for properties of the partial function implemented by the program. Rice's theorem does not apply to properties of the program itself. For example, halt on input 0 within 100 steps is not a property of the partial function that is implemented by the program. It is a property of the program implementing the partial function and is very much decidable. Gregory Chaitin has defined a halting probability, represented by the symbol omega, a type of real number that informally is said to represent the probability that a randomly produced program halts. These numbers have the same Turing degree as the halting problem. It is a normal and transcendental number which can be defined but cannot be completely computed. This means one can prove that there is no algorithm which produces the digits of omega, although its first few digits can be calculated in simple cases. While Turing's proof shows that there can be no general method or algorithm to determine whether algorithms halt, individual instances of that problem may very well be susceptible to attack. Given a specific algorithm, one can often show that it must halt for any input. And in fact, computer scientists often do just that as part of a correctness proof. But each proof has to be developed specifically for the algorithm at hand. There is no mechanical, general way to determine whether algorithms on a Turing machine halt. However, there are some heuristics that can be used in an automated fashion to attempt to construct a proof, which succeed frequently on typical programs. This field of research is known as automated termination analysis. Since the negative answer to the halting problem shows that there are problems that cannot be solved by a Turing machine, the Church-Turing thesis limits what can be accomplished by any machine that implements effective methods. However, not all machines conceivable to human imagination are subject to the Church-Turing thesis. It is an open question whether there can be actual deterministic physical processes that, in the long run, elude simulation by a Turing machine, and in particular whether any such hypothetical process could usefully be harnessed in the form of a calculating machine that could solve the halting problem for a Turing machine, amongst other things. It is also an open question whether any such unknown physical processes are involved in the working of the human brain, and whether humans can solve the halting problem. Representation as a set. The conventional representation of decision problems is the set of objects possessing the property in question. The halting set K equals program I halts when run on input X represents the halting problem. This set is recursively enumerable, which means there is a computable function that lists all of the pairs it contains. However, the complement of this set is not recursively enumerable. There are many equivalent formulations of the halting problem. Any set to whose Turing degree equals that of the halting problem is such a formulation. Examples of such sets include program I eventually halts when run with input 0. There is an input X such that program I eventually halts when run with input X. Sketch of proof. The proof shows there is no total computable function that decides whether an arbitrary program I halts on arbitrary input X, that is, the following function H is not computable. Here program I refers to the ith program in an enumeration of all the programs of a fixed Turing complete model of computation. Possible values for a total computable function f arranged in a 2D array. The orange cells are the diagonal. The values of f and g are shown at the bottom. U indicates that the function g is undefined for a particular input value. The proof proceeds by directly establishing that every total computable function with two arguments differs from the required function h. To this end, given any total computable binary function f, the following partial function g is also computable by some program e. The verification that G is computable relies on the following constructs: computable subprograms, duplication of values, conditional branching, not producing a defined result, returning a value of 0. The following pseudocode illustrates a straightforward way to compute G. Procedure compute_G. If f equals 0 then return 0 else loop forever. Because G is partial computable, there must be a program E that computes G, by the assumption that the model of computation is Turing complete. This program is one of all the programs on which the halting function h is defined. The next step of the proof shows that h will not have the same value as f. It follows from the definition of G that exactly one of the following two cases must hold: f equals 0 and so G equals 0. In this case h equals 1, because program E halts on input E. f0 and so G is undefined. In this case h equals 0, because program E does not halt on input E. In either case, f cannot be the same function as h. Because f was an arbitrary total computable function with two arguments, all such functions must differ from h. This proof is analogous to Cantor's diagonal argument. One may visualize a two-dimensional array with one column and one row for each natural number, as indicated in the table above. The value of f is placed at column I, row j. Because f is assumed to be a total computable function, any element of the array can be calculated using f. The construction of the function g can be visualized using the main diagonal of this array. If the array has a 0th position, then g is 0. Otherwise, g is undefined. The contradiction comes from the fact that there is some column E of the array corresponding to G itself. Now assume f was the halting function h. If G is defined equals 0 in this case, G halts so f equals 1. But G equals 0 only when f equals 0, contradicting f equals 1. Similarly, if G is not defined, then halting function f equals 0, which leads to G equals 0 under G's construction. This contradicts the assumption that G not being defined. In both cases contradiction arises. Therefore any arbitrary computable function f cannot be the halting function h. Proof as a corollary of the uncomputability of Kolmogorov complexity. The undecidability of the halting problem also follows from the fact that Kolmogorov complexity is not computable. If the halting problem were decidable, it would be possible to construct a program that generated programs of increasing length, running those that halt and comparing their final outputs with a string parameter until one matched. The length of the matching generated program would then be the Kolmogorov complexity of the parameter, as the terminating generated program must be the shortest such program. Common pitfalls. The difficulty in the halting problem lies in the requirement that the decision procedure must work for all programs and inputs. A particular program either halts on a given input or does not halt. Consider one algorithm that always answers, halts, and another that always answers, doesn't halt. For any specific program and input, one of these two algorithms answers correctly, even though nobody may know which one. There are programs that simulate the execution of whatever source code they're given. Such programs can demonstrate that a program does halt if this is the case. The interpreter itself will eventually halt its simulation, which shows that the original program halted. However, an interpreter will not halt if its input program does not halt, so this approach cannot solve the halting problem as stated. It does not successfully answer, doesn't halt, for programs that do not halt. The halting problem is theoretically decidable for linear bounded automata or deterministic machines with finite memory. A machine with finite memory has a finite number of states, and thus any deterministic program on it must eventually either halt or repeat a previous state. Any finite state machine, if left completely to itself, will fall eventually into a perfectly periodic repetitive pattern. The duration of this repeating pattern cannot exceed the number of internal states of the machine. Minsky warns us, however, that machines such as computers with e.g. a million small parts, each with two states, will have at least 21 million possible states. This is a 1 followed by about 300,000 zeros. Even if such a machine were to operate at the frequencies of cosmic rays, The eons of galactic evolution would be as nothing compared to the time of a journey through such a cycle. Minsky exhorts the reader to be suspicious. Although a machine may be finite, and finite automata have a number of theoretical limitations, the magnitudes involved should lead one to suspect that theorems and arguments based chiefly on the mere finiteness of the state diagram may not carry a great deal of significance. It can also be decided automatically whether a non-deterministic machine with finite memory halts on none of, some of, or all of the possible sequences of non-deterministic decisions, by enumerating states after each possible decision. Formalization. In his original proof, Turing formalized the concept of algorithm by introducing Turing machines. However, the result is in no way specific to them. It applies equally to any other model of computation that is equivalent in its computational power to Turing machines, such as Markov algorithms, lambda calculus, post systems, register machines, or tag systems. What is important is that the formalization allows a straightforward mapping of algorithms to some data type that the algorithm can operate upon. For example, if the formalism lets algorithms define functions over strings, then there should be a mapping of these algorithms to strings. And if the formalism lets algorithms define functions over natural numbers, then there should be a mapping of algorithms to natural numbers. The mapping to strings is usually the most straightforward, but strings over an alphabet with n characters can also be mapped to numbers by interpreting them as numbers in an NARY numeral system. Relationship with Gödel's incompleteness theorems. The concepts raised by Gödel's incompleteness theorems are very similar to those raised by the halting problem, and the proofs are quite similar. In fact, a weaker form of the first incompleteness theorem is an easy consequence of the undecidability of the halting problem. This weaker form differs from the standard statement of the incompleteness theorem by asserting that a complete, consistent and sound axiomatization of all statements about natural numbers is unachievable. The sound part is the weakening. It means that we require the axiomatic system in question to prove only true statements about natural numbers. The weaker form of the theorem can be proven from the undecidability of the halting problem as follows. Assume that we have a consistent and complete axiomatization of all true first-order logic statements about natural numbers. Then we can build an algorithm that enumerates all these statements. This means that there is an algorithm n that, given a natural number n, computes a true first-order logic statement about natural numbers such that, for all the true statements, there is at least one n such that n yields that statement. Now suppose we want to decide whether the algorithm with representation A halts on input I. By using Kleene's T predicate, we can express the statement A halts on input I as a statement H in the language of arithmetic. Since the axiomatization is complete, it follows that either there is an n such that n equals h, or there is an n such that n equals h. So if we iterate over all n until we either find h or its negation, we will always halt. This means that this gives us an algorithm to decide the halting problem. Since we know that there cannot be such an algorithm, it follows that the assumption that there is a consistent and complete axiomatization of all true first-order logic statements about natural numbers must be false. Variants of the halting problem. Many variants of the halting problem can be found in computability textbooks. Typically, their undecidability follows by reduction from the standard halting problem. However, some of them have a higher degree of unsolvability. The next two examples are typical. Halting on all inputs. The universal halting problem, also known as totality, is the problem of determining whether a given computer program will halt for every input. This problem is not only undecidable, as the halting problem, but highly undecidable. In terms of the arithmetical hierarchy, it is complete. This means, in particular, that it cannot be decided even with an oracle for the halting problem. Recognizing partial solutions, there are many programs that, for some inputs, return a correct answer to the halting problem, while for other inputs they do not return an answer at all. However, the problem, given program P, is it a partial halting solver, is at least as hard as the halting problem. To see this, assume that there is an algorithm PHSR to do that. Then it can be used to solve the halting problem, as follows. To test whether input program X halts on Y, construct a program P that on input reports true and diverges on all other inputs. Then test P with PHSR. The above argument is a reduction of the halting problem to PHS recognition, and in the same manner, harder problems such as halting on all inputs can also be reduced, implying that PHS recognition is not only undecidable, but higher in the arithmetical hierarchy, specifically complete.